女士们、先生们，有请上海国展展览中心有限公司总经理吴江红先生。Ladies and gentlemen, please welcome James Wu, General Manager, Shanghai Intex Exhibition.
Welcome to the second day of CES Asia. It is my pleasure to introduce our first keynote of today, offering you some fascinating insights into Horizon Robotics advancements and applications for the future of artificial intelligence. Dr. Chang, who co-founded the company in 2015 and is now Executive Vice President of the company, is at the forefront of the artificial intelligence revolution. A leader in edge AI processors and computing platforms, Horizon Robotics is a cutting-edge and highly innovative brand that is in the process of disrupting the computing industry with its advances in edge computing. And I'm very excited to hear from Dr. Huang. Now, ladies and gentlemen, please join me in welcoming Dr. Huang to the stage.
Thanks for the introduction, James. And 接下来我用中文
and Chinese Mandarin. Dear attendees, I'd like to thank you very much, and thanks to the organizers for CES Asia for offering me this great opportunity to deliver a presentation on the development trend for our edge computing and AI chips, and also who we are, Horizon Robotics. Some of the contributions we're making in this area. My name is Chang Huang. I'm the co-founder of this company. First, let's begin with AI democratization. Just like the left side of the chart shows you, this is a Ghana curve, which I'm sure you're familiar with already. Gartner, a very well-renowned think tank and consultancy firm, every year they launch this tech trend curve. So this curve indicates from a birth of a technology to the rapid growth to plateau and a bottlenecking all the way till the maturization and a steady growth of the technology, the whole life cycle of a new technology. I remember back in 2011, out of the Gartner curve, the first time we saw the adoption of AI, mainly into voice recognition. Voice recognition was the area where AI began to be adopted. Then after that, we have been witnessing increasing number of AI-specific technologies and applications. So on this curve, in August of last year, the newest Gartner curve was released. So if you zoom in on this curve, there are a whole host of factors regarding AI. For example, AI path and edge AI, autonomous driving, AI robotics, and convolutional deep learning neural network. So in the consultancy firm's report, for the first time ever, this company has launched the term, namely AI democratization. What does it mean? It means this technology is going to enter into every nook and cranny of the daily fabrics of people's daily life. So throughout this process, what kind of challenges we may be facing? One of the important challenges lies with the exponential and crazy growth of data. Then how can we process those data? And then the processing power it entails is going to be huge. Taking the year of 2017 as an example, globally, the data generated worldwide was around 5 PB. It is estimated that by 2025, it's going to skyrocket to around 40 PB, up by a factor of 8. Amid all those data, those new data, most of which are generated out of IoT. and a lot of them are non-structured data, for example, voice and image, those raw data, as a matter of fact, which you cannot effectively process. You have to structuralize them, for example, through AI computing, analytics, interpret the semantics and attributes of those data. Then you can mine the value of those data. So the structuralization process entails a lot of computation. So we have way more data generated, and it takes way more computing power and a computational muscle to do the processing. 25% of those data are in real time. You need to process them quickly. For example, those data related to autonomous driving and real-time traffic. On a second level, or on an order of magnitude of a millisecond, you need to be able to process those data. So this day and age, the data is mainly applied into commercial analytics, which are not very demanding for immediacy and not that mission critical. But going forward, close to 20% of the data is going to be closely related to our survival. Those are going to be mission critical data that we need to use caution in analyzing those data. We need to make sure we can process those data in a real-time manner. Then we have a 5G, which is a buzzword in recent couple of years. And efforts are underway to deploy 5G. I'm sure some of you have already got a taste of the charisma of a 5G in some pilot areas. In comparison to 4G and 3G, 5G raised the bandwidth of a transmission and a lower latency down to the millisecond order of magnitude. So improvement big time. However, on a backbone network, there is a problem. For a 5G base station, for each station, they can cover the perimeter of hundreds of meters in the proximity and access from those devices. However, there is no way for us to transmit those data from the devices efficiently to the cloud for processing. So just around the 5G stations, there is a barrier lake effect that will be created. A lot of data around the devices and their edge, which entail real-time processing. So they're pretty much stuck around the edge. There is no way for you to effectively send them to the cloud. Then this is edge processing comes in. So this is why edge computing is a must-have. Intel once put forward the slogan, MEC may not entail 5G. However, MEC is a must for 5G. MEC stands for multi-access edge computing. So when computing, multiple devices accessed, then quick processing enabled. To materialize 5G without multi-access edge computing, the 5G is not going to be that valuable, because the problem is there is a lot of pile up of data with inability to effectively process them. So the MEC is very important.
Take autonomous driving, a very typical edge computing scenario. A driver may be equipped with more than 10 cameras, capturing images every second with millimeter wave radar and many other sensors. There are data generated from the external environment and interior. For so many data, is it possible to transmit them to the cloud and then feed back the decisions to the car? Of course, the answer is negative. So, without a shadow of doubt, the
车辆每天能够产生多少数据呢？600。
The predominant number of data have to be processed at the edge. Every car needs to store sometimes data stored in hundreds of hardware storage. And with over 2,000 vehicles, the number of data generated is 2.5 million bytes. That is equivalent to the number of data generated by the entire humankind in 2015, such a staggering number. In the next 10 to 15 years, this is both an opportunity and a challenge. It makes edge computing something very necessary. What is the feature of edge computing? It is indicated by the chart on the right. First, high availability. It is able to operate offline without connection to the cloud. And computation can happen on board a car. Second, compliance. And compliance to privacy laws, especially. As I said, the data can be redacted at the edge, and it is only those data that are meaningful for the analysis and decision-making are used. Number 3, for the mission-critical applications, it is very necessary to ensure that the cost of data storage is lower and the transmission necessary is decreased. What is more, as we all know, we need to have V2X, especially V2 road, by connecting the vehicles with the roads and the infrastructure. And it is only by doing so that the system can operate effectively and efficiently. Edge will happen not just in a car, but also in a road. It could be on every sign, it could be on every traffic light. And latency is another thing. But I want to go back to transmission. We should not underestimate the cost and energy consumed transmitting data from the edge to the cloud. It is very important. And if we unravel the picture and break it down to 3 elements, and put the 3 elements on this coordinate with the dimensions of computational power and the feature of real time. Cloud, first of all, has the biggest spatial temporal coverage. It is really hard to tell which scenario is connected to the cloud. A cloud can process something that is generated from the other side of the world. So it needs universal architecture because it processes the biggest variety of scenarios and data. But it also needs to operate or process the biggest amount of data. That means it needs to have the greatest computational power. But in terms of real-timeness, of course, because of architecture, the latency is on the order of seconds. This, on the other hand, is the biggest bottleneck of cloud computing. What about devices or embedded devices? For each embedded device, it is located at a specific scenario. Unlike the edge, the embedded devices are used in a specific ROI so that it is very specific. And the architecture can be very specific too. The advantage is that architecture and algorithm can be designed specifically for the scenario. And it is very specialized so that the computational efficiency is the highest. I understand that you know this trade-off very well. If a model is trained on the cloud, then this model can be deployed on the devices, collecting data, making inference, reaching decisions and conclusions on the basis of which further decisions can be made and judgments can be made. But in the middle of cloud and devices, there is a new species, so to speak. It is just like a new layer between cloud, which is a huge node, and devices, which are like neural nodes or leaves extending through the boughs of a tree. Then edge computing is just like a spine that connects our brain, which is the cloud, and the neural nodes that are the devices. So edge computing has the features both of the cloud and devices. Its computational power is less than the cloud, but is far better than the devices. And it also fares better than energy consumption. It is completely acceptable to have 10 watts or hundreds of watts. And its latency is a lot lower than clouds. It is very important when 5G technologies are deployed. You will find then that the latency on the edge is a lot lower and more acceptable. So edge generates more possibilities because it combines the advantages of both clouds and devices. So conventionally speaking, it is the devices that are connected directly to the cloud. However, as I said, there is an explosive growth, exponential growth of data generated from the devices that can't be transmitted to the cloud. And that is why edge is very necessary to be on the receiver end of the data from the devices. And the edge can serve as a control valve or a filter that pass on the data that are a lot less than those generated from the devices and transmit these lesser data to the cloud, more important data to the cloud. It will lead to a paradigm shift, and it will lead to a complete revolution, both in terms of software and hardware. So I covered a lot of advantages of AI democratization, but on the flip side, well, because there are two sides to every coin, with so many data generated, maybe people haven't realized that there is a huge burden imposed on the society. Energy is a very important resource. According to the Chinese data center energy consumption white paper, in 2018 in China, there were 400,000 data centers of various sizes. On average, the annual energy consumption is 250 kilowatt hours. Taken together, they consume around 100 billion kilowatt hours. Any idea about that? It is equivalent to the power generated of the Three Gorges power station and the Gezhouba power stations put together. So this is a gigantic number. And according to our statistics, the majority of the costs in a data center is not the capital expenditure, but actually computation, cooling, everything that is about keeping the data center running account for 45%, nearly a half of the total costs of a data center. And the energy consumption per unit area or per square meter in a data center is 100 times higher than that of the offices. So we need to try various means to lower the energy consumption. For example, by putting the data center at Zhangbei, something done by Alibaba, because Zhangbei is very windy and average temperature there is around 3 degrees Celsius, so that cooling can be more efficient. And in my hometown, Guizhou, which is featuring big data nowadays, it is very mountainous, it is very cool in all time every year. So a lot of people place data centers, including Apple there. And there is a data center built in the Arctic Circle. And the 1/10 of the power of the Three Gorges power station will be consumed by this data center in the Arctic Circle, but it is already a lot lower because the cooling doesn't require a lot of energy. Such a huge amount of power consumption has huge impact on the environment. If every kilowatt hour emits 0.96 tons of carbon emissions, then last year the total number of data centers generated 9.6 million tons of carbon emissions. And this is equivalent to 2 times of the carbon emission of the aviation industry. People are talking about driving lesser cars and flying lesser planes. However, it goes unexpected by many people that the power consumption of the data centers generates so many carbon emissions. In the future, considering the number of data generated will grow exponentially, the carbon emission landscape is simply unacceptable. So it is a social responsibility of the AI and internet-based companies that we not just train and utilize these AI algorithms, but also we need to make sure that they run at extremely good efficiency, because it is only by reaching the extremity or in terms of effectiveness and efficiency that we can maximize the value given a limited amount of energy. I heard a story about Transformer, the best machine translation model by Google. Its name is Transformer. Google has deployed hundreds of machines using architecture search algorithm to train these hundreds of machines for a month to have the model. And the carbon emission is 284 tons, which is equivalent to the annual carbon emission of 5 cars. I've done the calculation. In-house, we need more than 2,000 kilowatt hours to train a big algorithm. But it's just about training. If we deploy them at the edge for inference, you may find that power consumption goes up by hundreds, thousands, of tens of thousands of times. So value creation is necessary. But on the other hand, we need to work very hard to lower the power consumption. So in different times, we use different indicators. For example, in the industrial era, we use the indicator of the power consumption to gauge the level of development of a country or of a region. And in the digital era, we see how many works are carried out on the cloud. That's another indicator. But in the future, maybe we can look at the utilization of AI to gauge the level of development of a country. But is it enough to look at the computational power utilized? The computational power utilized is the most optimal scenario, because a lot of the computational power is wasted. It is only those that are effective computational power that makes sense. That means how many computational powers that are utilized for generating AI decisions. We have different indicators for that. For example, TOPS per watt, TOPS per dollar. There is another indicator under that category, utilization rate. That is how many computational powers that are converted to AI computation. And we've also got another indicator that is AI performance per TOPS.
这个算是
Let's look at the equation. The traditional chip industry, there is a classic term, namely PPA, standing for power, performance, and area. Power is like the power consumption of one chip. Performance, of course, literally per second, how many times of addition or subtraction you're able to do. The area defines the basic cost of a chip. Also, traditional chip industry is continuously trying to optimize PPA. But in the AI chip era, we need to redefine performance. We're not only supposed to only look at how many computations you're able to do per second. We need to look at the utilization of the power of computational power, how much of that can be contributed and converted into the real AI performance. On the left, it is a TOPS per watt and a TOPS per dollar. So we times these two, then we come up with utilization, meaning how much of that is converted for real into AI computing. Then how much of the AI computing is converted into AI performance. Then finally, under per unit kind of a power consumption, we come up with an AI performance. So the AI performance per TOPS, this computing power converted to real AI performance. So this is up to what type of algorithm you're going to run. And utilization is determined jointly by algorithm and a computing architecture, the hardware design on your chip, in order to make sure your algorithm can be up and running in an efficient manner. Interestingly enough, think about it, in the past decade or so, it was well known to you that AI algorithm has been evolving at a high speed. Up to now, the AI algorithm is continuously evolving over time. The x-axis refers to the time continuum for evolution of the AI. So the effective AI computational power and how much AI performance generated as a result. This is increasing exponentially. 5 years ago, we used VGG to do image classification. The conversion efficiency was rather poor. A lot of computation only leads to limited precision. But now, with an NAS, if you do search, you come up with better network structure with 1/10 of the prior computational power. We can come up with way higher precision and speed for AI performance. With the same level of AI performance we aim at, then we can reduce the requirements for computational frequency exponentially. This is due to the rapid evolution and the development of AI algorithms in computing. So we're proud of that. However, unfortunately, although in theory to deliver on the same AI performance, there is a drastic decline of the computational volume it takes. But the efficiency increase is based on more sophisticated and a complicated algorithm development and design. So the bar has been raised for design of the computing architecture. In the past, for generic kind of algorithm, we designed hardware and the computing architecture on a chip. Those kind of a traditional architecture is no longer good for the new trend going forward. The old day AI chip and architectural design is no longer fit for those new computing paradigms going forward, just like the curve indicates. So with the evolution of the algorithm, the utilization is decreasing. So one indicator is up while another indicator is going down. Sometimes the gain that you achieve is not good enough to compensate for the loss. So sometimes people prefer the conventional algorithm because if you try to adapt the newer algorithm, then it may be less efficient. That is the pain point. But what is the philosophy of our company, Horizon Robotics? Then we'd like to introduce to you who we are. Earlier on, the name of the company was Horizon Robotics, but in Chinese language, we only call it by the name of Horizon. So many people may think of us as a company producing robotics and robots, but no, what we produce is the solutions, like the brain of the robots, instead of the robots themselves. Compared to other AI companies, what is unique about us is we are centered around the hardware and a software combination, a computing platform. That's what we do. So as a result, we can better tell the future trend for AI algorithms. We are centering around those platforms, combining hardware and software. So based on our view on the future trend, we can reflect those future trends in the current architectural design in order to make our solutions futuristic and future-proof so that we are quite a good fit for the evolutionary path of the algorithms. And with a new algorithm, yes, the efficiency is higher, but utilization on our chip will not be compromised. So if you times these two factors, the efficiency in a chip, the software and the hardware combined, so the overall architecture we have is not only good for the current classic algorithms, but also future-proof. So this is a great characteristic of the things we do. So we're going to target critical algorithms for future key scenarios. We have to be selective. If you try to cover all types of algorithms, all types of scenarios, then that is no different from the generic computing architecture, which it is very hard for you to optimize. Our philosophy is product driven, then we agilely iterate and upgrade our architecture generations down the road. So we combine efficiency, effectiveness, and flexibility. So some key factors here, the chip structure, algorithm, and a compiler. For a compiler, it's like a translator to translate algorithms into the efficient command sequence on our architecture for execution. So there are critical technologies, for example, the joint optimization and the simplified command set design, elastic tension core, etc. All those are about the compilation technologies and a programmable process flow. Then we also have the compiler-based performance analyzer. We're able to tap fully into the potential of the chip to bring to full play the performance of the chip, like the data reading and computing and a data storage and how they're distributed temporally. If there's a blank on the chart, it means it is a period of time with a low utilization. The chart on the left, there are a lot of blank spaces in the middle, meaning low utilization of the device. Then, if we do not optimize our compiler, then with this kind of conventional wisdom, we're only able to process 10 frames of images per second. It's going to consume a lot of bandwidth, so the utilization of computing power is only 1/3. But with compiler, as indicated on the right side of the slide, based on the architecture, if we do optimization big time, then we come up with the utilization result indicated on the right side of the screen. The utilization of the computing power up by a factor of 3 from 1/3 to 84%. Then MB per frame processed, that is the bandwidth consumption, down to 36. The DDR off the chip has a huge storage, but on the chip the storage is limited. The bottleneck lies with the bandwidth, right, between on-chip and off-chip, just like the relationship between cloud and the edges. So bandwidth usually represents a huge bottleneck. Once we do this optimization, access and storage is no longer a problem, but computing is a challenge. We have already bring to full play the computing performance after optimization. Another example, how can we have a joint optimization of not only algorithm but also architecture? This is a public testing dataset named Cityscapes for high definition street image, pixel-based semantic segmentation. It can tell whether the pixel originates from a lamp pole or from a road or from some other objects on the highway like a vehicle, etc. So this is a public testing database, so those developers and the testers upload the data onto this platform. According to those publicly accessible data, we can choose those best performing solution and compare it with the Horizon solution. So the comparator solution, the chip is Titan XP, the GPU. This was mainstream a couple of years ago. The precision is 74%. The speed is 8 milliseconds to process every frame. Power consumption is around 100 plus watt for chip power consumption. And the area of the chip is around 400 square millimeters. A big chip, high cost. The GPU is pricey. Our solution, the proprietary Gen 2 processor we developed in-house, named Journey 2, targeting the scenario of autonomous driving. Our precision is 74.5%, which is pretty close to the comparator, and the speed to process each frame is 9 milliseconds. Power consumption is only 3 watts. The chip area is less than 50 square millimeters, very small. If you look at the algorithm performance, there are two measures, namely the precision and the speed. We're on par with the reference. But if you look at our power consumption and the cost indicated by area of the chip, there are a huge difference. So this is due to the algorithm, architecture, and a compiler. So we have the extraordinary joint or co-optimization combining not only algorithm but also architecture. On many tier 1 and OEMs, our solutions already begin to be deployed. This is for L4 autonomous driving visual sensing solution 360 with a 12 degrees and 8 regular type of cameras. We're able to cover the panoramic view 360 degrees surrounding the vehicle. We can enable great visual sensing technologies, for example, to detect the lanes on the highway. So our customer previously used a GPU solution. When it was installed on board the vehicle, the power consumption was a huge challenge, especially during summertime. If you drive the car for 1 hour, there is a big trouble for heat dissipation. You have to stop the car after running on the street for 1 hour. Later on, the customer chose our solution, which was based on FGA. What we need is 3 FPGA, of which the power consumption is way lower than the GPU. Our power consumption holistically is only 100 watts. Then plus our newest generation chip, the power consumption will be further dropped to way below 100 watts systematically. So it is good enough to be applied into the vehicle. This marks a huge technological progress. As a responsible AI company, tech firm, we are not blindly pursuing precision. We need to consider cost in the equation as well. With regards to power consumption, going forward, one of the biggest challenges for the whole society is going to be energy availability. Therefore, power consumption is a very important factor. All AI firms must consider for real those efforts to be put in place to reduce the power consumption. Moreover, if you look at the developers' angle, machine learning and AI, when it comes to software development, AI and machine learning renders a disruptive revolution to the software development. The traditional development for software was object-oriented programming. You divide those issues into subtopics, then you find a cure for each subtopic, then you come back to the system level for integration, commissioning, then you do further optimization on the part of each module. This is a traditional software development pathway. In the era of AI and machine learning, the conventional paradigm is disrupted. Now, it is data-driven approach with regards to software development. You need to collect the data as system inputs. You do tagging on those data in correspondence to the semantics. Then, what you need to tell the system is what are the inputs and outputs. Then, what happens in between is happening within the system. The whole process is highly automated. You do not have to segmentize or divide those kind of systems into pieces. This is like the end-to-end training. So especially this is particularly true for deep learning because deep learning is data-driven. So with data-driven approach, you do software development and programming.
And then we need to revolutionize the pool of tools for such a new model of software development. You need data, you need labeling. On the basis of that, you do training. And for the software development kits of Horizon, first of all, we have reference models for you to use. And then we provide mainstream training frameworks on the basis of which you do the training. or you take the trained model and then we convert it to something that can be run on the chip, because there are some specific architecture on our chips that need to have a fine-tuning of the model. And then we do compiling, we do validation, we do evaluation, and then we deploy them on the embedded devices or on the edge. Sorry, can I go back to the previous slide? Well, if you took notice of the previous slide, there were two things that are in light green. Data, user data, and the built-up applications. We've emphasized that these two things are what the users own. We don't need to touch on these things, the SDKs that we develop. But it's not enough, because that was very basic, and that is also something that most of the chip manufacturers or chip designers provide. It is just about conversion of data into models. Yet, the complete AI development cycle is way beyond that. So we need some AI platform tools, so to speak, to make sure that the development cycle needs can be met. It includes data, devices, and models. First of all, we need to collect, store, label, and manage these data. And then through deployment, debugging, fine-tuning, and demonstration for these data to be deployed in the devices and utilized by the devices. In the process of utilization, a lot more data are generated to further enhance the accuracy of the model. This is a closed cycle, and it needs to run effectively. In the past, it used to be in silos, and many operations and maneuvers need to be manual-based, and it is very low in efficiency and effectiveness. So we hope to develop a chain so that the entire process can be semi-automated or even fully automated. The automated management mechanism can be in place so that the closed cycle can run on its own. And there are several advantages. First, the speed is up. Second, the development threshold is down because the interaction interface is very intuitive. It's easier to learn. And then the development quality can be guaranteed because the process is standardized. And of course, we need 30% less development people. The time it takes is 50% less. What is more, those that are capable that develop on this basis can increase significantly. In the past, because AI has been all the rage, there are many research institutions and higher education institutions that have created AI departments and AI majors to try to train more talents on deep learning, machine learning. Yes, we can train people. That's okay. But another direction of efforts is to decrease the threshold of development. As I mentioned, you just go to the platform and use the toolkits. So nowadays, it takes just 1 to 2 days, and you get to grips of the most basic concepts, and you're able to use these tools to effectively develop AI capabilities, and your competency is on par with the very professional and specialized AI engineers. This chart is about the chain of tools that we wish to build in order to forge an ecosystem platform. If only training is provided, then it is very difficult. However, if we give you a reference model for you to develop applications on that basis, yet you can't change the basic or fundamental algorithm, then the solution cannot be tailor-made. For the democratization of AI, it poses a great challenge. AI can be used in a big variety of scenarios. However, the current algorithms may find it hard to adapt itself in all these scenarios. So for a specific task, mission, or scenario, frankly speaking, a lot of workloads are required to tune the AI capabilities. And a lot of long tails are engaged. If we can't improve on the margin costs, then AI can't be deployed in the wider areas, greater variety of areas. There are a lot of scenarios that are only in the long tail. So we have to make sure that we empower our partners to lower the development threshold, to enable design capabilities, to give the ability to many more developers, to empower our users, so that on the basis of this open ecosystem, on this platform, computational power can increase, development threshold can be lowered, and a lot more capabilities can be deployed in the great variety of scenarios and applications. And there are 3 stages of AI computation: perception and identification as the first stage. Second is modeling and prediction. Number 3 is cognition and decision making. Well, AI becomes more active and more perceptive when you go to the right. The perception and identification could be very objective. On the right is very subjective. But as a platform developer, perhaps we should focus on the left, something that is more objective, because these are the tasks that are universal and generic to the big variety of clients and users that we face. Of course, we need to empower them on the basis of their preferences, to empower their development capabilities, to tailor-make their solutions in their own specific scenarios. We face a lot of challenges. We have tailor-made software solutions as a challenge to be met. We have various algorithms. We also need to design architecture to decrease sophistication and level of complexity, which brings up cost. And I need scalability, lower costs, lower power consumption, higher computational power. So what should I do? We provide extremely optimized computational power on the basis of our architecture, and then we are able to connect you to our system. And we provide you with a lot of reference models for you to use, take and use, and then tailor-make your own solutions. So on the software side, it is very open. It empowers our users. And if we look at this, we have hardware, system, software, and then an intelligent application system. On all these 3 layers, Horizon Robotics does something that is generic and universal, something that everybody uses. For example, the AI processor, for example, our BSP, and the abstract layer of hardware. We also provide BPU SDK on the top layer, but it's not complete. We need to empower, as I said, our users so that they can develop on all these 3 layers to come up with a more complete and more full-fledged product of their own. This actually is the mission of Horizon Robotics. It guides us, maybe forever, in all the steps that we will take in the future. Our objective is to empower everything to make everybody's life safer and better. With our chips, our algorithms, our basic fundamental platforms, you will be able to explore the different applications together with us. And on the other hand, we position ourselves as the tier 2 supplier because we empower with regard to technology. We don't touch data, we don't do applications. That means we provide our users with ultra-high cost-effective AI chips. We provide you with things of very low power consumption. We empower you with our chain of tools. We focus on two big areas of application: autonomous driving and AIoT. These are the cases in point. It is about detecting the workers on the construction site and see whether they've got their helmets on their head. It is a very niche application. In China, there are 800,000 construction sites, and if every construction site needs 10 cameras, then we have 8 million needed. So the use volume is very low. The market is not that big, though the number may sound impressive to you, yet the devices needed in it may only be 1/10 of the maximum number, especially in the preliminary stage. Yet if your launch cost or if your marginal cost is a bit too high, then it's really hard to meet the needs of this niche market. However, with our platform, it takes less than a month to complete the whole development cycle for such a niche application. It is on the basis of the toolkits that we provide. It is, on the other hand, on the basis of the reference models and the models that we provide to our users for this to transpire. This is another case. We have a booth here at CES Asia. You can experience this on your own. We can, as you see in this case, to segment the image on the pixel level and make analysis so that the IDs of these in the camera can be detected. We can look at their emotion, their mood, their gender, their age. And of course, with regard to privacy protection, I can put a block on your face so that your face is blotted out, and only the blotted out image and the ID value is stored. That's protecting privacy, because only very few people understand what the ID value means. And even if you look at the picture with the faces blotted out, it's very hard, bordering on impossible, to know who he or she is. But if you deploy it on a cloud, it's really uncontrollable. So edge computing is very important. This is very amazing, and it's also fundamental to autonomous driving in the future, which is HD mapping. It is about establishing a map model. It is not something that you use on your mobile phone. It needs to be of very high resolution or accuracy. You need to detect one piece of bush, one tree. I need to know where a traffic light is, where a small obstruction is, or what the lane lines are, where the lane lines are, in order to guide the cars on the road. The conventional ways of collecting data and processing data is of extremely low efficiency and high costs. Yet we introduced a visual-based, data-based data collection module, and we worked with our Korean partner to deploy it in the application of smart cities. As you see on the picture on the left, we have a 3D dot cloud, point cloud, I mean. And people think that it is on the basis of laser radar. Yes, indeed, it could have been made possible only by the laser radars. However, what we have here are only a couple of very conventional cameras backed up by high-performing algorithm and processors to make sure that visual processing can replace laser radars to come up with the point clouds.
So we've managed to cut cost by a factor of 100 or more, so to make sure this technology can be deployed on a myriad of vehicles. The HD mapping on a daily basis or by hour or even by minute Those vehicles up and running on the street can continuously apply HD mapping and collect the data, compare between the HD mapping data and those other comparator data, and to transmit those filtered data back to the cloud for deeper processing. Right now, with our mobile phone, there is a real-time traffic condition with color codes telling you your ahead kind of a route, which section is going to be jammed, right? It is amazing already. But going forward, for each city, the whole city level high definition map can be updated not only on a monthly basis, but by hour or by minute. This is another example that we cooperate with our client. This is the Xiaoai smart speaker, a very important product of Xiaomi. So our voice solutions are integrated into the smart speaker. So a very challenging technology that we develop. If you say a sentence to the speaker, for example, if you call out aloud the name of the smart speaker like Xiaoai, then the speaker will pick up your voice and get to know that you're calling the speaker by their name. Then this speaker will be woken up and respond to you. This is a very big technical challenge we managed to conquer. And then we got certified by Amazon certification. In a standardized way, our solution can be deployed into millions of smart speakers going forward. Right now, we are having very close collaboration with Xiaomi through our solution. Then this is another example. We cooperate with a car OEM, talking about the multi-zone interaction. If you're a passenger on board the vehicle or even a driver, no matter which seat you're in, you're gonna have an independent voice-based and a vision-based interactional system with high level of precision. Although there is noise in the surrounding driving ambience, this system can suppress those noise in a very wonderful fashion. Because going forward, autonomous driving will emancipate the passengers, especially driver, from the driving work. So they're going to have more time spent on interaction, socializing, and learning, so on and so forth. You're going to find that in addition to mobile phone, the car cabin is going to be a very important traffic entry portal for internet traffic. This is why those internet giants are going all out, developing solutions targeting the onboard vehicle application scenario. This is the 96 Sports, a ecosystem alliance that we already joined, this year, and this is a very important kind of alliance. Then we join this community in order to accelerate AI enablement. So within this community, there are different modules and blocks, those different intelligent solutions and devices. So you can build those blocks, and then at a high speed, you can manage to come up with wonderful solutions. We actually joined 96 Sports Alliance this April, so we contribute our processor capacity into this community, so more developers will have access to our power in terms of edge computing. So our slogan is AI on Horizon, Journey Together. How can we explain or interpret this slogan? We're a platform-based company. We're willing to enable our various customers to develop their solutions across multiple scenarios so that they can mine the data and to turn those data into valuable information. So we enable our customers to do that. In the meantime, this is a joint journey, right? We actually march on this journey together with our customers. This is a long journey ahead. We never think of what we do as a party. We think of it as a long journey. If you review some of the work in the past years in the entrepreneurial circle in this country, There were flavors of the month, those party, those buzz, but some of the firms just died down later on. But we are dedicated to the long cycle. We aim at the long game, especially with regards to the chip business. By nature, it is a long game, so we are ready to work hand in hand and shoulder to shoulder with our customers on this journey together in order to mine continuously the values out of the AI. A little commercial at N3, the booth 3324. We have a booth there. Please feel free to drop in. The demos I already talked about in my presentation. Yes, you can review those information at our booth. I also welcome you to have a taste of our real-time demonstration. Please feel free to drop in on us at our booth at N3 Hall to find more about what are there for you based on edge computing. Thank you.